Hello, my name is Hong Zhu. I'm a professor of computer science at the Oxford Brookes University, United Kingdom. Welcome to my presentation of a research paper co-authored with my colleague, Dr. Ian Bailey. The work is concerned with testing classification systems, which is also called classifiers in the literature. Such applications are widely used in computer applications such as face recognition, object recognition, disease diagnosis, and so on. A number of AI techniques have been applied to develop this kind of classification systems. For example, clustering, which is unsupervised learning, and classification as a supervised learning. Testing AI applications is a grave challenge to software testing. A traditional technique for testing classifiers is the category partitioning testing. The basic idea of the testing method is to focus on the border between the classes. The test cases are selected on the border and nearby to the border in order to detect the border shift errors and the border rotation errors. However, this technique is not easily applied to AI-based applications because the borders between classes are often unknown. The data space and the borders are much more complicated than the traditional software. The errors made by the developers are not the same as what the developers would make in the coding of the program. So the error in this kind of classifiers are not necessarily the border shift or border rotations. However, the ideas of category partitioning testing can be applied to testing AI-based classifiers. For example, for a software that recognizes animals, we would like to test the software on different types of animals, but would be more interesting to test the software on animals that are similar to each other. For example, fox and wolf to be distinguished from dog, tiger to be distinguished from cat, and so on. The notion of similarity is a very important part of classification systems, although it may not be explicitly defined in a classification system. Mathematically speaking, the similarities between entities can be defined as a distant function that satisfies a set of mathematical properties. Therefore, a classification system can be formally defined as a mapping from the input data space to a group of classes. And there is a distant function defined on the input data space. Now we introduce the notion of a Pareto front as an abstraction of a test set that consists of test cases on the border and nearby to the border. Formally, a Pareto front is a set of data points in the input data space that each pair is in the different classes and the distance between them is small enough. For example, consider a classifier shown in the diagram here. An example parental front could look like this. Well, each dot on the screen is actually a pair of dots in the input space. They are so close to each other that they are visually inseparable. Now the question is, given a classification system, how can we generate a Pareto front to test the software? The idea we borrow is the so-called exploratory testing. Exploratory testing, the idea has been around for quite a while. However, we believe James Whittaker is the first person who did a systematic study of the testing method. His work is in the context of testing GUI-based systems. Whitaker defines exploratory testing as an interactive process in which the tester interacts with the application and uses the information that the software provides to change the course of testing in order to explore the application's functionality. It is fundamentally different from verification and validation testing. In this process, the testing is to discover what the software does, while in validation and verification testing, the purpose is to prove or disprove the correctness of software with respect to known requirements or specification. So, in exploratory testing, the software on the test is regarded as an unknown object, and it is subject to the experiment to find out what the object is. In contrast, in traditional validation and verification testing, the knowledge of the software on the test is essential to perform testing activities, including design the test cases and check the correctness of the result. Test cases in exploratory testing are not prescribed, they are generated or selected on the fly. They are used to guide the choice of the next test cases rather than treat the test case as independent to each other. Whitaker pointed out, for exploratory testing to be effective, it is important to follow certain test strategies. Generally speaking, a test strategy determines what, when, and how test activities are performed. He proposed a set of test strategies for manual testing of GUI-based systems. It is still an open question if software test strategies can be automated. The solution we offer here is datamorphic testing. It is a technique we proposed a year ago for testing AI-based systems. It is further developed by a recent paper we submitted to AI Test 2020. In this testing methodology, the artifacts in a software test automation are classified into two types. The first is test entities, which are objects and data that are used and or generated in the testing process. Typical examples of test entities are test cases, test sets, the program under test, and test reports, etc. The second type of test artifacts is so-called test morphisms. They are mappings between entities, mathematically speaking. They generate and transform test entities to achieve testing objectives. They can be implemented as test code and evoked to perform test activities. They can be composed together to form test processes. Typical examples of test morphisms include test case generators, data morphisms, test oracles, mutation operators, etc. In the framework of datamorphic testing, a test strategy can be regarded as a combination and a composition of test morphisms. They can be formally defined as a generic algorithm that uses various types of test morphisms and test entities as parameters. In fact, we have implemented 3 sets of test strategies in a test automation system that supports datamorphic testing. Morphy is the testing tool we have developed recently. More details of the tool can be found in our paper in AI Test 2020. In this paper, we propose 3 exploratory test strategies to generate parental front in order to test classifiers. They are random target strategy, directed walk strategy, and random walk strategy. The random target strategy consists of two stages. At the first stage, 2 points in the input data space are selected at random. If the 2 points are in different classes by the classifier, then we move to the second stage. In the second stage, we repeatedly take the midpoints of the 2 points that are in different classes for a number of times until the distance between the 2 points of different classes are small enough. Therefore, they can be included in the parental front. The directed walk strategy also consists of 2 stages. It starts with select 1 point in the input space at random, and then it applies a unary datamorphisms as a walking method to find another test case, and to see if test case is in the same class of the previous test case. If it's not, it will take another application of the same datamorphism to generate another test case. This process is repeated for a number of times until it finds a data in a different class. The last 2 test cases in different classes are used for the second stage to refine to find the 2 test cases are close to each other to be included in the parental front. The third strategy we propose here is a random walk strategy. It's similar to the directed walk strategy, but the difference is we use a number of different unary datamorphisms to walk through the input space until we found a point which is in a different class. In addition to use a number of different datamorphisms, the choice of which one to use is at random. Therefore, it is a random walk. Once we found 2 points in different classes, then we apply the same stage 2 algorithm to refine the test case to find the parental front. In the paper, we have give algorithms for implement these strategies and proved the correctness of these algorithms. We have also conducted experiments to study the factors that influence the effectiveness of these test strategies. Here, the test effectiveness is measured by the number of test executions required to generate each pair of border points in parental front. The subjects used in the experiments are on the same input domain but with different structure of classes. For each subject, we execute the algorithm on each pair of parameters for 10 times. The average of the data are used for the analysis of test effectiveness. The experimental data shows that for random target strategy, the average number of test executions increases as the number of walks increases. The size of a parental front also increases linearly with the number of walks increases. The test effectiveness increases as well with the number of walks increases. The overall test effectiveness varies significantly on different subjects of the test classification system. Similar results can be found for directed walk as well as random walk. To summarize, in this paper, we proposed a new approach to test classifiers by adaptation of exploratory testing. We further developed the datamorphic testing by introducing the concept of test strategy and formally define the strategy, implement the strategy in a testing tool. More details can be found in the paper for the algorithms, their correctness proofs, experimental data and the analysis, as well as comparison with related work and directions for future work. Thank you.